Hi, and welcome to Rosie's STEM. Today I'm going to be talking about an exam question from my Introduction to Data Science class that every single one of my students missed. We're going to also be talking about how that question is linked to a very famous question in probability known as the Monty Hall Problem. So during my Intro to Data Science course, we discussed probability. So on the exam, I have probability questions, and one of them this past time was this. Alba has two kids. Given that one child is a girl, what is the probability that the other child is also a girl? You can assume there are an equal number of males and females in the world. This was a multiple choice question, and I gave them four possible answers: 1/2, 1/3, 3/4, and 1/4. A quick note here, I am assuming that you have a basic knowledge of probability. If you want me to put out some videos on probability theory, comment below. I'm always open to hearing what content is helpful for you. So a very common approach to solving this problem is to first note that using the assumption, the probability of any single birth being a girl would be 1/2. And you can also note that two births are independent events, meaning that the sex of one child should have no effect on the sex of another child. So therefore, the probability that the other child is a girl should be the same as the probability that the first child was a girl, which is 1/2. So the probability of one being a girl, given we know another is a girl, shouldn't really be affected. It should still be 1/2. And this was the logic of most of my students that answered this question with A, 1/2. However, this is not actually the correct answer. We are missing the fact that we know that there are exactly two children, and we have information about one of those two children. A probability is calculated as the number of times an event occurs out of the total number of possible events. So you can start by writing out all of the possible events. In this case, there's four potential sex combinations of the children. Alba could have a girl and then a girl and then another girl, a boy and then a boy, or a boy and then a girl. But the question tells us that one of the children is a girl, so boy is actually impossible, leaving us with only three possible events, which will be the denominator of our probability. Of these events, though, only one results in the other child being a girl as well. So the probability is actually 1 out of 3 possible events, or 1/3. This question is a simplified version of a classic problem in probability known as the Monty Hall Problem. This problem is based on an older game show called Let's Make a Deal, and it's named after the show's original host, Monty Hall. So here is that problem. Imagine you are a contestant on Let's Make a Deal. Monty shows you 3 doors and tells you that behind one of the doors is a new car. Behind the other 2 doors are goats. If you pick the door with the car, you win that car. You pick one of the 3 doors. Monty, who knows what's behind all 3 doors, opens one of the 2 doors you did not choose, revealing a goat. He then tells you that you can switch your choice to the other unopened door. To have the highest probability of winning the car, should you switch to the other unopened door or keep your original choice? It's tempting to think that each door has a 1/3 chance of being the correct door when you first selected a door. And now, since there's 2 remaining doors, each should have a 1/2 chance of containing the car. This approach is similar to the logic in our first approach to the Alba's children problem. But just like in that question, we are ignoring a key piece of information. So Monty is not opening a door completely at random. He actually knows what is behind all 3 doors. So when he opens a door to show you what's behind it, he purposefully is choosing a door that he knows contains a goat. This means that he purposefully did not choose the other door, increasing the chance that that is the door that has the car. So if you're ever on a game show like this, always switch doors. It actually increases the probability of you winning. But this problem is kind of hard to wrap your mind around, so I've come up with a couple of different ways of explaining it that should help you see why that probability increases. First, we can actually just brute force our way through the calculation like we did in the Alba's children problem. We can list all possible choice combinations and count how many times that leads to the event of us winning the car. So if we want to do that, we first have to think through the different places for the car to be. So there's 3 different doors, 3 different places the car can be. In each of these 3 scenarios, you also have 3 possible options for choosing a door. And in each of those scenarios, you have 2 options to stay or to switch doors. So listing all of this out is a bit harder than it was in the Alba problem. So let's break it down into smaller pieces. First, let's go ahead and assume that the car is behind door 1. That means that goats are behind doors 2 and 3. If we choose door 1, Monty is either going to open door 2 or door 3 to reveal a goat. It doesn't matter which of these he opens. Either way, you're going to want to stay with door 1 because door 1 gets you the car. You were lucky enough to pick the correct door the first time. Let's make a tree out of this. So if the car is behind door number 1 and you choose door number 1, then you have the option to either switch or stay, no matter which is the unopened door. You don't want to switch, you want to stay, right? So what if you actually chose door number 2 instead of door number 1? In that case, Monty would have to open door number 3 because door number 1 contains the car. He wants to reveal a goat. So the other unopened door would be door number 1, and that's the one that has the car. So you don't want to stay with door number 2. You're going to want to switch. That's what's going to get you the car. Now, finally, if you chose door number 3, it's similar. So if you choose door number 3, Monty has to open door number 2, which means you again want to switch to door number 1. We can do this for the scenarios when the car is behind doors number 2 and 3 as well. So when the car is behind door number 2, again, you only want to stay if you chose door number 2. If you chose door number 1 or door number 3, you'd want to switch. And if the car is behind door number 3, it's similar. You only want to stay with your choice if you chose door number 3. If you chose door number 1 or door number 2, you want to switch. So the only times that you actually want to keep your original choice are when you were lucky enough to choose the correct door the first time. Putting this all together, when you don't know where the car is, it's always best to switch doors because there are more times that switching doors would lead to you winning the car. In other words, it's best to switch doors because this increases your probability of winning from 1/3, from just randomly picking 1 out of 3 doors, to actually 6 out of the 9 potential events, or a 2/3 probability of winning the car. Here's another way to think about the problem. Imagine you are choosing between 100 doors instead of just 3. The only time that you wouldn't want to switch would be if you were lucky enough to choose the correct door the first time. Do you really think you're lucky enough to choose 1 door out of those 100 doors that contain the car? Once Monty opens all the other doors but 1, let's say he's opening them 1 by 1 to reveal goats, you should certainly switch to the door he purposefully chooses not to open at the very end when you have just 2 options, because he's not choosing that door for a reason. There's most likely a car behind it. Okay, so that is the famous Monty Hall problem. I think if there's one takeaway from this problem, it would be to really think through what every potential option or event is in a probability problem like this, If it's possible to list them all out, you should, even if you have to do it using tree diagrams like we did here. It'll help keep you from missing important information in the problem. What do you think is the key takeaway from the Monty Hall problem? Comment down below. If you have any more useful ways of thinking about this problem or questions about the problem, please comment those down below as well, along with anything else you'd like me to cover in future videos. And if you found this video helpful or interesting, please like the video and subscribe to my channel for more content like this. And I will see you all in the next video. Thanks for watching.